Now, if I were to take this sponge and I rub it against the surface, I will be able to trap all the dirt and the grime on that surface. But now, what if I told you that instead of trapping the dirt, I now trap an anti-cancer drug? So first thing is, metal organic frameworks, or MOF for short, they can do exactly that. So they are just simple structures made up of two components. So firstly, you've got a metal part. So what you see up there is a metallic powder. This is then bound to an organic component. So basically, any structure that has a carbon in it. And what's so unique about this is that if I were to take a small component of it and put it under a microscope, you will see that it contains lots and lots of pores, just like the sponge I showed you. Now, when a material is highly porous, what this means is that if I were to take that material and put it into some other substance, it will be able to soak up large volumes of that substance. And if you ask me, how much can it soak up? That is equivalent to the size of a typical football court. And that is about 5,350 meters square in about 1 teaspoon of MOF powder. That's massive internal surface area. So since MOFs have this high porosity and large internal surface area, scientists have been recently using this in the areas of gas detection and gas storage. But now, can we apply these MOFs for a much more noble cause? Let's say if we look into the treatments of trying to solve a disease that's been plaguing humankind for decades. The moment I say that, one of the diseases that will easily come to your mind would be cancer. Now, if you start going into the solutions and treatments for cancer, there are going to be plenty of them. And one of the most common treatments that patients undergo is chemotherapy. And chemotherapy is a method wherein patients are injected with small dosages of toxic drugs over a long period of time. And now, because you have this issue of not being able to track how the drug moves around the body, what happens is that as a result, lots of patients suffer from various different kinds of side effects. So then this got me thinking, well now if MOFs have such a large internal surface area, can I now use the MOF to trap a lot more drug at once? And now that you have lots of drug in there, can I tweak something in the structure of the MOF to now be able to monitor how it moves around the body? And this was what I came up with. Now it looks very complicated, but the only thing you need to look at is manganese. So manganese is a metal that is naturally present in your body as a micronutrient. And manganese is also used as a dye in cancer diagnostics such as MRI scans. So bam, now you have a MOF that is able to load a lot more drug at once, so which means it can deliver a lot more drug to the tumor site at once, so making it therapeutic, and you can also monitor how it moves around the body, which means it's diagnostic. Essentially, you've got a theranostic tool. Sounds really easy, isn't it? But here's the problem, right? You have about 160 chemotherapeutic drugs in the market, and you have about 1 million organic molecules to pick from. How do you know which combination works the best? How do you know that my MOF is not just the sponge, but it's actually a Scotch-Brite? So then I thought the most efficient way to overcome this is now to tap on the expertise of technology, where now you just sit at a desk and you computationally model these structures. So instead of spend years of energy, money, and time in a laboratory trying to design these MOFs, you sit at a desk, you tell the computer program, hey, I want to look at these parameters, I want to change these physical factors, and then you study how the MOF interacts with the drug that you've chosen. So now you've got a much more simpler, cost-effective, and efficient method of designing a MOF. So the next time you're in your kitchen washing your dishes, and you look at the sponge in your hand, remember that this sponge is way more powerful than you think it is. Thank you.